All right, so today we're going to talk about how to analyze an actual circuit. And to do this, we're going to mostly use Ohm's law, the V equals IR that we talked about last time when we were talking about currents and resistors. But then we're also going to add a couple of little hints, a couple of little rules that will help us figure out what is the current through any particular device that we're looking at, or we might want to know what the voltage is, or we might want to know what the resistance is. So if I know any two of those, I can figure out the third. Probably one of the most important things that we can do with this, though, is figure out the current. Because when you've got a robot, for example, and we've got our main board, and I'm attaching these devices to it, that's going to change the amount of current. And I can't have too much current going through my main board, otherwise I'm going to fry the thing. So we don't want to just connect stuff up and hope it works. Instead, we always lay out a diagram for it. We say, okay, here's how much current is going through each of these devices. Is it going to be safe? So that's going to be our main goal. I'm going to introduce the rules that we're going to use, Kirchhoff's rules, and then we're just going to spend most of this session just simply looking at a typical circuit and figuring out what the current's going through. All right, let's get started. All right, so here's how we're going to do it. We've got a basic robot setup here. We've got the microcontroller, that's the main board. This is where the robot's brain is. Down here, then we've got a sensor, some sort. Maybe it's an ultrasonic sensor. Maybe it's accelerometer, doesn't really matter. And then we have a left and right motors for them. Now, we can idealize each one of these things as a load. And a load just basically acts like a resistor. Now, in the case of the microcontroller, there's a lot that goes on inside that. But ultimately, when I figure out how much goes in and how much goes out, that gives me a resistance of everything inside. And so that's why we can treat that load as a resistance. So anytime you see the word load, you're really thinking about a resistance, even though it may not be a physical resistor there like we talked about last time. All right, so these devices are wired to a 5-volt power supply, which is pretty typical for an Arduino main board. Most of them can only handle about 5 volts. And so we want to know what is the current going through each of these devices. And we list here the maximum. So, for example, let me switch to my black pen here. There we go. So, for example, the maximum current for the main board itself is 7 milliamps. And remember that an amp is a measure of current, so it's coulombs per second. And this would be obviously 10 to the minus 3. For the sensor, we're going to say there's 4 milliamps, and then each of the motors is going to be 5 milliamps. So given this setup, it's plugged in, hypothetically, and it's running. How much current is going through each device, and is each one of them safe? That's what we want to find out. So we're going to use Ohm's law with that, but I don't have just one device in a circuit, so really have to think about this. So we've got two rules that we're going to follow. These are called Kirchhoff's loop rule and junction rule. And so this first one says, if you look right here, the first one says the total current into a junction must equal the total current out of a junction. Now a junction would be something like what you see right here. So I would have, let's choose a different color so that we know what we're doing. So let's say that I have current going this way. We're going to talk about that in just a second. Then the total current coming out of this bottom one here plus the top one must equal the total current that went into it. And that makes sense, really. This is, if you think about it, that's nothing more than our statement of charge continuity. Since current is the charge moving, in order to keep from losing any charge, the stuff that goes in has to equal the stuff that comes out. And you can also think of that maybe as water pipes, right? If I've got water coming in and it splits into two pieces, well, part of the water goes left and part of the water goes right. So that's going to be what's happening with this particular design up here, all right? So that's what the first rule says. The first rule says simply charge continuity. Current in must equal the current out. Same thing, if I have multiple currents coming in, that must equal the total current coming out for the same reason. The next one is a little bit more complicated, but we've actually already talked about this. So the total potential change around a loop is 0. Let's briefly draw our capacitor circuit that we were working with before. So here's my battery, and I'm going to show you the proper symbol for the battery in just a minute. But this is the one that we've used before. So if this was 9 volts, we said that this was 9 volts. So if you think about it, as I go around the loop here, I may produce 9 volts, and then I'm going to store that 9 volts around there. So the total around here has to be 0. So this law is nothing but a statement of conservation of energy. since the potential, the electric potential, is really just the electric potential energy, it's not going to be created or destroyed. So if I have a fixed circuit, I'm not changing anything, I'm not moving capacitor plates or anything like that, then energy has to be conserved. So that means the total potential change, which would be the same as the total potential energy change around the loop, any loop, has to be the same. The only thing that's different here, if I can erase this, since we're not going to need that, the only thing to think about here is I've got more than one possible loop. So for example, I could do the big loop here, and the total change around that loop would have to be 0. So if I add up all of my potential, so I'm going through here and then down this one and then this one. So I'm not going through these the sensor and the left motor one. That would be one loop that must add up to be 0. Another possible one would be this loop right here, even though there's no voltage source there. So you see my voltage source here is 5 volts, but the change around that loop must also be equal to 0. So we're gonna work with all of these different possible loops, and really the art of solving this is to get the same number of equations as unknowns, just like in our problems that we can solve with our scenario solving procedure. So you're just going to be looking for equations that building up by using the loop rule and the junction rule until you have everything that you need. You've got the same number of equations as you have unknowns. Then we're just going to solve the simultaneous equations. Now, I will warn you, it could be simultaneous equations with 5 variables in it. And so that gets to be a lot of manipulation and a lot of steps, but it's just algebra. It's not difficult, it's just time consuming. So that's the big thing that you want to kind of keep in mind is that, yeah, you expect that I'm going to get all my equations. I'm going to have to solve one of them for one of my variables, and it's going to be in terms of all the others. I'll plug that into this, solve for another one, take what's left there, plug into the third one, solve for all those, and so on and so on. And so there's lots of places that you can make sign errors. The biggest thing about this is take it slow. Double check your signs each time, because there's nothing more frustrating than getting to the end and realizing somewhere in all of this algebra you made a sign error. Check it as you go. All right, so there's a couple of rules that we need to keep up with for our sign conventions, and those are given down here. Let's zoom in on that for just a minute. So if we cross a resistor in the direction of electron flow, which remember is the opposite direction from the current. So let's draw us just a quick circuit here. Let's say I've got a resistor and a battery. Now, for the battery symbol, they are just like you put in the battery upside down. And I don't like that that's how it is, but that's how it is. So if you remember the physical battery, this was the positive end and this was the negative end. So you would think this would be the positive end, but it's not. This is the negative end, and that's the positive end. And really the best way to remember it is it's opposite of a physical battery. As long as you remember that, you're going to be fine. Okay, so if we cross a resistor in the direction of electron flow, then it has a positive potential change. So ask yourself, what direction are the electrons moving around this circuit? Are they going clockwise or are they going counterclockwise? Pause the video and think about it, because this is a key part. All right, well, the electrons are going to be repelled from the negative end of the battery. That means that this direction must be our positive direction. That's the direction that the electrons are going. So if I cross my resistor, for example, in this direction, then I'm going to get a positive potential change. On the other hand, let me just erase this part and this part. On the other hand, if I cross the resistor in this direction, now I'm going to get a negative potential change. And that potential change is simply determined by Ohm's law, V equals IR. So if I know what the current is, and so I'm going in the direction, so I'll find out what current I have here, multiply that times the resistor, and that's going to be my potential change. Now, here's the confusing part. Remember that, let's suppose the way we've got this wired up right now, our electrons are moving this way. Which direction is the current? The current, and get my camera back, my current is actually going this way. It's the direction positive charges would move. So, but I find that difficult to keep up with, because then I've got too many backward things I have to swap. So the way I would remember the rule is, if I cross it in the direction of electron flow, which in this case is opposite to the current, let's get my camera back, which is opposite the current, then I'm going to have a positive potential change. All right. You'll see how that works in just a second. All right. And the second thing then, so now if we look at the same circuit, but now we're going to talk about crossing a battery. Now, just as a reminder, we've got it here. The long line is positive. So remember, it's the opposite of a physical battery. This, you think of the bump on the battery as being positive. Well, okay, unfortunately, the symbol's drawn backwards. So that's negative. So if we cross the battery from the negative terminal to the positive terminal, so that's this way. So I'm going around the loop in this direction. Then we consider that to be a positive change in voltage. So if this is a 9-volt battery, I would say that was plus 9 volts. Right? Because I'm crossing the battery from the negative to the positive. Now, if I need to go the other direction, so let's say that I'm going from the positive to the negative, which means I'm going around the loop this way. So that's going to be the opposite. And so then I would say this would, for example, be a negative 9 volts. And the plus or minus sign is just talking about what direction I'm crossing the battery. And that just makes the algebra work. So it's important that we remember these sign conventions. Write these sign conventions down your flip book and keep referring back to them. We're going to practice that when we're here, but make sure that you're remembering, if I cross the resistor in the direction of electron flow, then the potential change is positive. If I cross the battery from minus to plus, little to big, then I get a positive potential change. So if you remember, with the negative charges and from negative to positive, those are going to be your positive cases. All right. So let's try this for real then. Let's zoom out here. Okay, so here's our example then. And what we want to do, let's write up our scenario, is we want to find the current through each device, including the main board. So here's my microcontroller, here's my sensor, my left motor, and my right motor. And then we're going to make sure that we don't fry. We got to make sure that this thing is going to be less than the maximum that they can stand. Okay. So we are going to need to come up with some labels here. We've got let me zoom in on that just a little bit so you can see it a little bit better. And you see that I've got A, B, C, D, E, and F. It's a good idea to go ahead and label all of your junctions. The reason for that then is that will let you talk in your equations using these as subscripts. All right. So what we're going to do, we need our minimum loops. Now, a good rule of thumb is anytime you add a loop, you need to put a new component in there. What happens a lot of times is you'll think you've got a different equation. And it turns out that it's just a modified form of an equation you already have. And so it doesn't help you. You're still short one. Well, okay, that's not tragic. You just go back and find another loop and put it in there. But so the minimum loops in this case, let me go into red, that we could possibly use is I want to use the voltage source. And then through, whoops, I don't want that to be a straight line. Whiteboard's not doing me a favor here. So, and then I'm going to go through A and then through F and back. So that's going to be one of my loops. So we'll call that loop VAF. That's going to be one of my loops. All right. So that's one. I'm going to get rid of these so that we don't have too many lines coming back and forth through here. So the next loop that we might look at, so you saw that loop included the microcontroller and the sensor. So I want to add a new component with this. So one might be using, let's use a different color so we can see it, using A, C, D, and F. That would be one that we could use. And you see that I've added this new component in here. This one we've already used, but I've added a new component here, adding in that right motor. So I might use A, C, D, F. All right. I'm just recording these so we know what to go back and look at. All right. Another one that we might use might be A, B, E, F. And you see that while that uses the sensor, it adds in the left motor. So that would probably be one that's going to work for us. So that's going to be A, B, E, F. That's going to be another loop. And then I've got a choice. I need one more. Right now I have 1, 2, 3, 4 unknowns. So I need 4 equations. Now, I need one more loop, right? But I don't have anything that's going to add anything to this. So, any other kind of loop I could do, like say I decided I wanted to use B, C, D, E, like this. Do you see that that doesn't add any new components? And so chances are that's not going to be a unique equation that's going to help me. So most of the time, you're going to want to use the junction rule at least once. And we could use it at any junction we want, but so let's use the junction A. So coming in here and coming out this way. So we know that the current coming into A must equal the current coming out of A. And so from AB and then to AF. So we will say we'll use the junction at A. So these are going to be loops, and this will be my junction. All right, so that's basically how I'm going to set it up. I'm going to set up all of the equations then, and then I'll be able to solve all of this that I want. All right, let's let's see, I guess we better zoom out a little bit here. Okay, so we need to define our quantities. And let's talk about the current across the microcontroller, right? We'll call that, I think I use the symbol IM, make sure that it matches my notes here. So this is the current across the microcontroller. So that's the current through here, through this point right there. And then we will talk about the voltage across the microcontroller. We'll talk about the current across the sensor. The voltage across the sensor, and you should write all these out. These are not technically going to be unknowns, right? Well, these are going to be unknowns that we're going to put into our simultaneous equations for that. And then I'm also going to have the left motor and the right motor. So we'll say ILM. This will be the left motor. And of course, I have a voltage, LM. And then I'm going to have an I for the right motor. We'll call that voltage RM. The battery voltage, I'm just going to call V. So anywhere where I have V, just plain V with no subscript, we're talking about that 5-volt battery there. Then we're also going to have the 4 resistances that we know. So we'll call RM is going to be 400 ohms. That's the microcontroller. RS is going to be 300 ohms. That's the sensor. RLM is going to be 500 ohms. I'm sorry, it's going to be 200 ohms. Oops. RM is going to be 200 ohms for the left motor. And finally, RM is going to be 200 ohms for the right motor. And those should be all of the variables that I need. And I've done that just by saying, okay, I'm probably going to need the current and the voltage for every single one of these. And then we're going to go through with that. All right, now when you're setting up your equations then, in our design, we've reminded ourselves of what loops we're going to use. So all we need to do is be very careful about our signs. So let's jot down our sign conventions here. So if we cross a resistor in the direction of the negative charges, which is not the current, that's the opposite direction from the current, be very careful about that, then the change in voltage is going to be positive. And then the second sign convention rule is that if I cross the battery from negative to positive, then the change in potential is positive. So those are the rules that we're going to use. All right, so let's start writing out some equations. And I don't quite have enough room to get all the equations that I need here. So let's put this to the side. Let's see, I'm running out of space. Let's put this to the side over here, I guess. And let's see if we can get all of our equations in one place. Oops, I want the other one in front. There we go. Whiteboard's a little tricky that way. Okay, so let's write down our first loop. So our first loop is the battery. Let's do that in red. Our first loop is going to be the battery, and then through A, and then to F, and back. Now, it doesn't matter which direction you choose, because all of these have to add up essentially to be zero, right? The total change around the loop has to be zero. So it really doesn't matter. So why don't we go clockwise? We'll just decide to go clockwise. And you can also start anywhere you want. Why not start at the battery? So we're going to start right here. Is this the negative end or the positive end of the battery? It's the negative end, because it looks like a AA battery here, but the bump now is backwards. So this is the negative end, and this is the positive end. So I'm crossing from negative to positive. So what is my voltage here? Is it positive or is it negative? It's going to be positive because of this rule here. So my first equation then is going to be positive V, and then I'm going to come around here, and now I'm crossing the resistor. My negative charges are going this way. Do you see that? So I'm going to choose, so I'm crossing it in the opposite direction. Let's see if that makes sense. I'm going opposite the direction. So I'm going, this is actually with the current, right? Because that's the direction the positive charges would move. If I had gone in the negative direction this way, then moving across this resistor would have a positive voltage. But I'm going in the opposite direction. I want to give you practice. We're going to do it both ways. So I'm moving in a positive direction. So I know then that my voltage change, let's do that in red. I know that my voltage change is going to be negative the current through the microcontroller times the voltage through the microcontroller. I'm sorry, times the resistance through the microcontroller. Let's get that symbol correct. And that's because V equals IR. That's where that comes from. So I'm adding up all my voltage changes. So this, the I times R, that's just the voltage across this value right here. All right, then as I come down, I'm going to go through this one. I'm through the sensor. I am still going against the flow of the negative charges. Right, so my negative charges are going counterclockwise. I'm taking this loop clockwise. So that means it's also negative. And so then the current through the sensor times the resistance of the sensor. And all that has to equal to zero, because now I'm back to where I started from. Let's make sure that we would get the same thing if I went in the opposite direction. I want to convince you that it doesn't matter. So now we're going to go counterclockwise. Let's start again with the battery. This is positive and this is negative. So I'm crossing the battery from positive to negative. Well, if I cross from negative to positive, then I'm going to get a positive voltage change. So that means I must be getting a negative voltage change. So that's V, negative potential difference. Now as I go across the sensor here, the electrons are moving this way. I'm moving in the same direction as the electrons. So that means I'm going to get a positive I sensor plus R sensor. Now I'm going to go through the microcontroller. And again, I'm moving in the same direction as the electrons. So that's going to be a positive I microcontroller times the resistance of my controller, and that's equal to zero. And you see that if I multiply through by -1, I get exactly the same thing. So either form of this is going to give you exactly the same answer. All right, then let's continue to walk through this, and let's look at our other loops that we're planning to do. All right, the next one we decided was going to be ACDF. And so if I'm going this way, so it's going to be, oh, I'm sorry, ACDF. We're going to do this one in a minute. So we'll do ACDF. Notice I don't have any voltage sources, but which way is the current going? which way are the negative charges? So this is negative, so my negative charges are going this way. So the way I've drawn the loop again, I'm going backwards through it. Now I could just as easily go through the loop the other direction. So let's try that this time. I want to show you that it doesn't matter which way you go. As long as you're consistent with your signs, it's all going to work out. So my electrons are going this way. So let's go around the loop this way. Now we only have two devices here. So I have the right motor, and I'm going with the electrons, so with the negative charges. So that means I'm going to have a positive I right motor times the resistance of the right motor. Nothing on this branch. Then coming down through here, I'm also going with my electrons, though, are now going this way. Do you see that? That's a little tricky. Let me draw that in a different color so that you can see it. So as I leave the battery, my electrons are going this way, and we all agree that they're going this way. But now they have to split and go this way. Does that make sense? So think about that pipe. The water comes in here, and then it splits. So my electrons through this branch are actually going up. So now I'm going in the opposite direction from that. So that means it's got to be negative IS times RS, and that has to equal 0. If you're not sure about that, stop the video, pause it, and think about it, and see if you can work through it. All right, our next one is set to be ABEF. So that's this small loop here. Remember that my electrons are going this way and this way. So as my electrons here, they're going to be going up like that. So it comes in here, it splits, and goes like that. All right, so going around the loop then, nothing in this branch. Coming down this way through the left motor then, I'm going opposite the direction of the electron, so it's going to be negative. So I've got I of the left motor times the resistance of the left motor. Nothing on this branch. Coming through this branch, I'm going through the sensor. I'm going with the electrons. So I'm going this way. Notice that I've got to get 0 at the end of the day, which means chances are usually one of them is positive and one of them is negative. Otherwise, it's going to be very hard to get 0. Because each of the letters here, they're just magnitudes. So that's a good rule of thumb. That's a good way that you can kind of protect yourself with that. All right, so there's 3 of our equations. Okay, so I have done the first 3 loops. So all that's left now is to talk about the junction at A. So my current coming in this direction, let's do that in red actually. So my current, this is my negative charges, but my current is going this way. Does everybody see why? Because that's a positive and that's a negative. Current shows the direction of the positive charges. We hate Ben Franklin. And that must equal what's coming out. So I know that the current through the microcontroller must equal the current through this left motor here. I'm sorry, through the sensor. Let's do that one first. Plus the total current that's going through these two, right? So that's going to be the current that's coming through this branch right there. See if that makes sense. Let's stop and think about that. So in the end, it's going to go through both this motor and this motor. You see how the current has to go through both? It's not just going through one, it has to go through both. So the sum of that must be I left motor plus I right motor. That's a little bit tricky. Let's stop and think about that and see if it makes sense. So the current comes into junction A. It goes out through each of these branches. And this one's pretty obvious. Here, though, there's no component here, right? However, that component, that branch right there splits into 2 components. And all the current has to go back through there, and then it has to come back together. All the current that splits this way must come back together before it hits the battery again. Because continuity, I can't lose anything. So yes, I split in these 3, but then it has to come back together. So that's why I have to add all of them. So now V is a known. It's given to me. all my resistances are known. Those are given to me. I have 1, 2, the motor, the sensor, the microcontroller, the sensor, the left motor, and the right motor currents are my only unknowns. I have 4 equations and 4 unknowns. I'm ready to go. So at this point, the physics is over. There's nothing to do but solve these simultaneous equations. I would suggest that you actually try this on your own. Pause the video. See if you can isolate each equation. So pick one, solve for a particular variable, use the expression you get for that to plug into another equation to solve for that. And you'll have eventually gone through all 4 equations and you'll have one variable equals a whole bunch of knowns. Figure out what that is, plug in your knowns, get that variable, then put it back in the previous one, and so on and so on. Pause the video and see if you can do that. Then come back and let's do it with me. All right, hope you tried it because there's a lot of work that goes into this and you really do need the practice for it. All right, so let's start then. So we started off by wanting to get rid of the left and right motors. So I'm going to start off with this one here that uses the left motor. So I'm going to do I LM R LM plus IS RS equals 0. And even though it's not obvious on each one of these because it was on the previous page, these are all equal to 0. There we go. So I want to get rid of that left motor. So I want to isolate it by itself because what I'm going to do is I'm eventually going to plug that in somewhere else. So I'm going to move it to the other side. And that tells me that I get IS over RS is equal to positive, let's just go ahead and explicitly write it out, positive left motor over right motor. And so I want to divide, left motor here. So I want to divide by that. And so I get that the left motor is equal to current through the sensor, resistance of the sensor divided by the resistance of the left motor. Like that. And then I can do the same thing for the right motor. So I've used this equation. That one's done. Now let's go up and do the same thing for the other equation. And this time I've got positive I right motor, resistance right motor, minus I sensor, R sensor equals 0. Again, I'm going to solve this for the right motor. So I get IS RS, move that to the other side, equals positive I right motor, R right motor. And so I right motor is equal to IS RS over R right motor. I'm sorry. Yes, that's correct. Over R right motor. All right. And so now I've used this one. Remember, I can only use each equation once. All right. So the next thing we're going to do is we're going to get the microcontroller mode current in terms of the sensor current. I already know what these are. I already know what these two are, so I can plug those in. So let's use our junction rule here. So I know IM is equal to IS plus ILM plus IRM. Like that. Okay, and we're going to solve for the sensor current here. And so that, I'm going to isolate that. So we're going to solve for IM. Get my facts straight for what we're doing here. Is IS plus, now I need these, IS RS over RLM plus IS RS over RRM. And I took that from these 2 places up here. I'm going to factor that out just a little bit to make this a little bit easier. And so I get IS times 1 plus RS over R left motor plus RS over R right motor. Now, yes, it's true that these are the same, but I actually wouldn't combine those just yet because they generally won't be the same. So we want to learn the technique for this. Okay, so I have now used this equation. So the only one I have left then is the top one. And so hopefully this is going to fill in everything I know. So we'll start off with V minus I microcontroller, which I just found an expression for that, times the resistance of the microcontroller minus IS RS. So by the time we're done, the only thing that's left should be IS. Okay, so let's plug in for what we know. Let's plug in for IM, and let's get it in terms of IS. Now, there's going to be a lot going on here. Let me hide this real quick. going to be a lot going on here, so we want to make sure that we're being very careful with our signs and our parentheses with that. All right, let me go to my black pen then, and we'll start with this over here. So I'm going to get the V by itself just to start off with. So I'm going to get V minus, let's plug in for IM first. So that's going to be IS plus IS RS over RLM plus IS RS over RM. You see what I've done from this part right here? I've just multiplied my IS through all of that. And all of that is then times RM, and then minus IS RS equals 0. So let's move all of these that have the IS's in them. Let's move everything to the other side. So I'll have V then is equal to, I'm going to multiply through by my RM, and that's going to be positive RM IS, and then of course this whole expression right here is going to be positive. Keep that in mind when I move it to the other side. So that gets rid of all my minus signs, which should be nice and easy for me then. And so then I'll have plus IS RS RM over RLM plus IS RS RM over RRM. I'm running out of room, plus IS RS. I'm going to factor an IS out of all of that, and I get V is IS times RM plus RS RM over RLM plus RS RM over RRM plus RS. And so all we've done here is we've tried to isolate our IS, and so then we'll divide all of this by that. And so I get RM plus RS RM over RLM plus RS RM over RRM plus RS. And so that's equal to our sensor current. That's the current that's going through the sensor right now. Okay, so now you know all of these values. I'm not going to take the time to multiply them out, but you should be able, you know that the voltage is 5, and we know the resistances for all of these. And you should find that IS works out to be 2.63 milliamps. Let me write this over here a little more neatly. So IS works out to be 2.63 milliamps. You would then take this value of IS and plug it back in and find, you've got a couple of choices, a couple of ways that you can do this. You could plug it into IM because we know everything for that, and that would certainly be okay. I'm going to push this back in just a minute. I also know IS, so I can find ILM just as quickly. And in fact, those actually would go a little bit faster. So I can plug in for the ILM and the IRM and get IM. It's up to you. If you want to work out this value multiplied by the IS you just got, then you would find that IM is going to be equal to about 10.5 milliamps, and you should find that ILM is going to be 3.95 milliamps, and of course IRIM is the same because it's got the same resistance. And it doesn't matter which of these you find first. If you add up IS, ILM, and IRM, that had better come out to be equal to IM by the time that we're done. So now we go back to our original circuit then, and we see, do any of these cross the limits? Well, the microcontroller is going to be a problem, right? The maximum voltage, the maximum current our microcontroller could handle is 7 amps. And we're going to be running 10.5 amps through it. So we just fried our board. The sensor is okay because it needs to be less than 4. The motors are okay because they need to be less than 5 milliamps. So what happens then is when we connect the sensor and the motors at the same time, we try to draw more current out of the microcontroller than it can handle. So what's going to happen with your microcontroller is going to brown out. It's going to shut down, and then it will spontaneously restart, but it won't execute your program. And so your robot will just kind of be sitting there dead from that. That's if you don't fry it to begin with. So going through this analysis before you actually turn on your robot is very critical. And if you think about expanding it up to the level of space shuttles and aircraft and things like that, it's even more important because you've got thousands and thousands of systems all interacting at the same time, most of which are all coming out of the same power source, the same voltage source. So you got to make sure that your airplane's still going to fly. Okay, so I've cleared out the whiteboard here so that we can talk about one more thing. We spent a lot of time solving those 4 simultaneous equations, and it does take a lot of time. Now, imagine if you had even more components in there. It's going to take a long time. This method will always work. You can always work out the loop rules for a bunch of different components, solve them simultaneously, and you'll be done. However, there are shortcut ways that we can take, and that's what I want to teach you now. And generally speaking, this is what you're going to want to use when you're trying to solve one of these circuits anytime you can. We need a few preliminaries there first. So let's take a look. Let's suppose I have a circuit, and we're just going to keep a nice simple one with a battery here. And then let's suppose that I have 2 light bulbs. But instead of wiring them in series, I'm going to wire them parallel to each other. And we'll draw our little light bulb symbol here. Right, and we'll call this light bulb A and light bulb B creatively enough. Okay, so those are all connected there. So when they were in series, we had, and I'll just kind of draw that right quick over here, all the current that came into this bulb went into this bulb, and all of it came out. That's the definition of being in series. If all the current goes in and all the current comes out of the same spot, then we say that they're in series. And we know that if this is resistance A and this is resistance B, well, then we found that the total resistance was just the sum of the two. And that always holds when I have pieces in series like this. Now, in this case, though, the current comes in here, but we know by the charge continuity principle, some of the charge goes here and some of the charge goes here, and then, of course, down through B. So the current that's going through A here cannot be equal to the current that's going into that junction. And so but we can say that the sum of the currents going into must equal the sum of the currents going out. So let's say that this is the total current. Then I can say that I total equals IA plus IB. If you think about it, that makes sense. Charge is real. Charge is a thing. And so it hits this junction right here, and then it splits. And some of the charge goes down here, and some of the charge goes through here. All right. So now I want to come up with what happens with the resistors. Now, obviously, we assumed if they were going to be in series that all the charge went through, and that's not happening here. So if I have these two in parallel, I need to take another look at it. So let's start with the current rule here, with this branch rule it's called. And let's substitute in Ohm's law for that. So remember, Ohm's law is V equals IR. So I must be equal to V over R. So this is microtask 1 in your book for this section. All right, so we're going to replace all these. And so I get V tot over R tot must equal VA over RA plus VB over RB. However, let's think about what is happening to the voltage here. Now, we probably can all agree that if this is V, if this is the voltage, then the voltage across A must be equal to B, because these are just wires, right? They're just wires connected to it. But the same thing is true for B. It's also directly connected to the battery, and so therefore it's also getting the total voltage. So that says that all of these 3 voltages that you see here are the same. So let's just divide them out. And so I get 1 over R total equals 1 over RA plus 1 over RB. And this is the expression for adding the resistances when the resistors are in series. I'm sorry, when the resistors are in parallel. This is for series. Let's make sure we're clear on that. That's for series, and this is for parallel. Now, notice that it's 1 over R total. A lot of students want to just do 1 over RA, 1 over RB, and say, okay, you're done. Don't forget you have to flip them. Now, if you really, camera back, if you really want to, we could go ahead and flip this. And so that would tell me that our total is equal to 1 over RA plus 1 over RB. So we need to get a common denominator here. And so that says our total is equal to 1 over RB over RB. That's my common denominator, plus RA over RB. I'm going to add those up. Our total is going to be 1 over RB plus RA over RB. Well, when I take 1 over that, I'm just going to flip it. So I'll write it out here where it's a little more clear. So it is also true that our total is equal to RB over RA plus RB. Either way works. They're exactly the same. I find it a little easier since my calculator has an invert button. So 1 over x or x to the minus 1 might be on your calculator. I can take the resistance, hit that button, plus the next resistance, hit that button, equals, and then hit the button one more time and it'll flip it for me, rather than having to think about all these complicated operations. But as always, you do you. That's all fine. Okay, so now that I have this expression for parallel and series resistors, I can actually use that to find the equivalent resistance of any network configuration that I want to work with. So let's go back and let's figure out what's going on with our original circuit, our microcontroller and the sensor and the robots. Now, we've got to think about some characteristics of this. When I have two loads in series, what happens to the total resistance? Well, it's going to go up. I'm just adding them. What might not be so obvious is that if they're in parallel, the total resistance is actually going to go down. It's going to be less than either one of the originals. And so it's actually going to decrease. So if this were, 100 ohms and this were 200 ohms, when I wire them in parallel, the total resistance here must be less than 100 ohms. And so that's one reason why trying to wire too many things into your circuit can actually cause a problem. I generally want them in parallel. That way, if for some reason this one dies, the other one doesn't die as well, which would happen if they were in series. But the more loads I add to the circuit, the lower the total resistance is actually going to be, which means for the same voltage, I'm increasing the current. And so if I increase that current draw, well, if my robot can't provide it, then it's going to brown out or it's going to fry from that. So this is a really useful thing to keep in mind. If I put them in series, the resistance goes up. If I put them in parallel, the resistance goes down. With those two, you can make any kind of resistance that you want. All right, so let's go back to our original circuit here, and I'm going to sketch it again here. So we had a battery that was like this, and then it went through the microcontroller, and then through a sensor, through the left motor, and through the right motor. And then it all came back together. So this was the resistance of the microcontroller, which we said was 400 ohms. This was the resistance of the sensor, which we said was 300 ohms. That's a 3. Funny looking 3, but it works. And this is the resistance of the left motor, and then we can call that RLM if we want, or just RL, which was 200 ohms, and the right motor, which was our RM, or just RR, which was also 200 ohms. Okay. Now, we found all our loops and we solved it. We know what the answers are, and you can go back through the video or hopefully in your notes and you can find out what those are. But let's reduce this circuit down to a single voltage source and a single resistance. And you can almost always do that. And so that will always help you. Sometimes you're going to see that we can actually just solve the entire circuit this way. So let's do that. So our first task then, and let's do this in red, is to combine these three resistors, these three loads, into a single resistor. Well, we know that 1 over, and maybe we'll call this resistor RLR, or SLR, for the combined sensor left and right motors. That's going to be 1 over RS plus 1 over RLM plus 1 over RM. And we're going to work that out. So this is going to be 1 over 300 ohms plus 1 over 200 ohms plus 1 over 200 ohms. Pause the video, put that in your calculator, work it out, and let's see what you get. Wait, you should have found, again, get my camera back. You should have found that the total resistance was only 75 ohms, which is considerably less than any of the three together. So this is my RSLR. So what I want you to do then in the next block down in microtest 2, where we're working with this, we want to combine all of those into a single resistor, but then we're going to redraw our circuit. And that's kind of important that you redraw your circuit to keep up with what's going on. So I'll put it over here. So I still have my battery. I still have the main board, but now I have a single resistor, single load that represents the combined load of everything here. All right, so this then is our, now we've got two RMs, don't we? Better be careful about that. This is SLR, there we go. Okay, so now ask yourself, are these in series or are they in parallel? Well, they're in series, and you know that because all the current that goes in here comes out and then goes into the next device. So if they're in series, I'm going to use the series formula for that. So R, we'll call this MSLR since it's everything, must equal RM plus RSLR. Well, now we know what these are. That's pretty simple. This is 400 ohms, and this is 75 ohms. So the total resistance must be 475 ohms, just like that. All right, so now at the very bottom of that microtest, let's redraw the circuit one more time. You should have just one battery, one voltage source, and one load. So here's our battery. And then I have one load that's the combined load of all four of these components. And so I know that that combined load, SLR, is 475 ohms. And this, of course, is still just 5 volts. Let me see, okay, well, how does that help me? Because I want to know what they are individually. Okay, so first of all, let's figure out what the current going through the entire circuit is. And hopefully you agree that because of the charge continuity principle, the same current is going through every little branch of this simple little circuit here. So let's work out what that current is. What should I use? Okay, well, if you're not sure, we're following along in microtest 3. You're going to use Ohm's law for that. So we know that V equals IR. And so that then if I'm going to solve this for I, then I, which we'll call maybe MSLR, must equal the voltage divided by the resistance of MSLR. There. And so that's 5 volts divided by 475 ohms. Pause the video, put that in calculator, and see if you get something familiar. Okay, well, when you worked it out, you should have gotten 10.5 milliamps. 10.5 times 10 to the minus 3 amps. That number should sound real familiar. Let's see if we can figure out what's going on. So we know that the current through the battery is 10.5 milliamps. So we know that that's true everywhere through the circuit. That's also true here. Let's go back to our original circuit. So this is 10.5 milliamps. We'll put our amps in there. Well, by the charge continuity principle, the current through the main board must also be 10.5 milliamps because all of that charge goes straight into there. So now without doing any simultaneous equations at all, you just found that R of the main board is 10.5 milliamps. Go back, check with your notes, see if you got the same thing after all that work. So this helps us in a number of ways. Sometimes I can, like you're going to see here, I can just keep going and I won't have to do any simultaneous equations at all. But even if I do have to do simultaneous equations, having one more known, even one, reduces the number of equations I have to work with. So let's say I needed 4. If I managed to find the values of 2 of them, well, now I only have 2 simultaneous equations, which is actually quite a bit easier to figure out. Okay, so we now know that our motor is 10.5 milliamps. Now, that doesn't really help me much with this one because that's just a whole bunch of things together. And same thing here, that's a whole bunch of things together. That's all 3 of these. So let's take what we know then and let's find another loop. Because remember what our rule is when we're, go back to eraser. What our rule is when we're trying to find the currents, we always have to add one more component into the loop, one new component that wasn't in the loop anymore. This is how I managed to keep from reusing equations, which of course will just put me going around in a circle. It won't help me at all. So let me kind of gently erase this right here so that we can easily draw our loop. Okay. And so this then is RS. So we now know what RM is. We know that RM is 10.5 milliamps. I know that this is still the voltage. It's still 5 volts. So can you find a loop that adds just one new component and hopefully only has our two knowns and has no other unknowns in it? Well, let's draw that in a little multicolor. This loop right here is going to be an obvious choice, right? You see, we know this, we know RM, we know the voltage. So all that's left is to find that RS, which is the only unknown. Well, I don't need simultaneous equations for that, do I? So let's use the loop rule. And the way I've chosen this, I'm going across the battery from negative to positive. So is the voltage positive or is it negative? It's positive. Okay. Now, my electrons, remember, are going out this way. They're being repelled from the negative end. So as I go across this resistor, my electrons are coming back this way. But I'm going around the loop this way. So I'm going in the opposite direction for the electrons. So that means the voltage there is negative. Remember, always use Ohm's law. So instead of just writing the V of this, I'm going to write it as IM RM. But you should see that that's just the voltage. Okay, now I'm going to come through here. I'm still going against the electron flow because the electrons are coming up this way and then they branch up this way. Because remember, they're going to split. I'm going to have some going up each one of these branches here. That's what makes them in parallel. So that means it's going to be negative, and I'm going to have, let's do the current first just to keep them the same. And I'm going to have IS over RS. And then I'm back to my voltage source, so that's equal to 0 by conservation of energy. So this is Kirchhoff's loop rule. Now, I know everything in this equation except for IS, which is what I'm looking for. So let's solve for that very quickly. So I want to move the IS to the other side, and so I get V minus IM RM equals IS RS. Then I'm going to divide through by RS, and that tells me that V over RS minus IM RM over RS is equal to IS. Let's put in what we know. We know that the voltage is 5 volts. We know that RS is 300 ohms. Minus, we now know the current through the main board is 10.5 times 10 to the minus 3 amps. Remember, we have to work in amps, not milliamps. And then that is multiplied by the resistance of the main board, which is 400 ohms, and divide by the resistance of the sensor, which is 300 ohms. Okay. So pause the video, put that in your calculator, work out what is the value of IS, of the current through the source, through the sensor here. All right, well, when you do the math, you should get something that looks like this. I'll put it back in red up here. You know what? We said that was R. That's actually I. Can't have a resistance that's measured in milliamps. So let's change that. So our main board current was 10.5 milliamps. The current through the sensor was 2.63 milliamps, which should be exactly what you got before. But we found it directly without a whole lot of algebra that we had to do. All right, so now we need to add another loop. Now you've got some choices here. It may be obvious to you that, well, okay, I'll just go this way and add a loop. And it would work because you're only adding one new component in there. I know the voltage, I know what RM is, I know what IM is, and so just adding that is going to be perfectly fine. So it's a good exercise for you to do it that way. But let's consider that there might be a simpler loop. So let me do undo here. What about this loop? So you see, I know the current through RS now. I just found it. So now the only unknown in this circuit is RLM, or RL we've been calling it. And so that's going to be really easy. So let's look at which way the electrons are coming. They're going up the branch here on both sides. Convince yourself that it's on both sides. The electrons are not going around in a circle, and that's where a lot of students get confused. All right, so let's write down our Kirchhoff's loop rule for that then. And I'm going to do it in the direction that we've drawn here. So I'm going to go clockwise around the loop. Remember, it doesn't matter as long as you're careful with your signs. So when I cross RS, I'm going with the direction of the electrons. And so that means that's going to be positive. So IS, RS, remember it has to be a voltage. And so that's positive. We said, I'm going to put that positive there to remind me. When I come back through here, when I go through RLM, I'm actually going in the opposite direction. So that's going to be negative. So that's going to be IL. We'll just call that RL. And then I'm back to the beginning, so that's 0. And you see how that's a very, very fast and simple equation. I want to solve for IL. So I have IS RS equals IL RL. Divide both sides by RL. And that tells me that IL is going to equal to IS, that is an S, RS over RL. Very quick and easy. All right, so we're going to see what that is. That tells me that the left motor must be 2.63 times 10 to the minus third amps. Don't forget to convert back to amps. Times the resistance of my sensor, which is 300 ohms, divided by the resistance of the left motor, which is 200 ohms. All right, pause the video, work that out, see what you get. Okay, so you should get 3.95 milliamps, exactly what we had before. Now you can probably say, oh, I can see that these resistances are the same. And so whatever current I have that comes in this way has to evenly split up those two branches. And that's fine. So we know that both motors are 3.95 milliamps, just like you found before. Let's go ahead and record this up here. So IL equals 3.95 milliamps. Okay, but what if they weren't the same? Well, I can still do the same thing. I can take the easiest loop then would be to just use this loop, right? So let's work it out, even though it's not going to change anything. We know what we're going to get, but it's good practice for us. So going around the loop then, now I have positive ILRL minus IRRR equals 0, which tells me that ILRL equals IRRR. Remember, I'm looking for the R, IR. And so IR must equal IL times RL over RR. Well, I know IL is 3.95 times 10 to the minus 3 amps. I know that RL is, well, 200 ohms. And I know that RR is 200 ohms. And so you see that's 1. And so IR is still equal to 3.9 milliamps. But now we've proven. And not only that, if they're not the same, you know what to do. So you see that by solving this circuit, by reducing it down, made us go much faster. What took us 45 minutes to do with algebra, we were able to do in 10 or 15, even with me just explaining every single step. You could probably go through this on your own much faster now that you see what we're doing. So the rule is then always, always, always reduce your circuit as far as you can. In almost every case, you can reduce it to one voltage source and one resistor. There are some outlier cases, but in most cases, we can reduce it to a load and a voltage source, and that's it. So do that. That will always simplify. Maybe you won't even have to use simultaneous equations at all. However, even if you do, you've found some knowns. So you're going to have fewer equations because you have fewer unknowns. And that's a very powerful technique. Okay, so hopefully you see that most of the work in these types of problems is actually not the physics. It's actually the algebra. Setting up the physics, as long as you're careful with your signs, is actually fairly straightforward. That's why you'll find a lot of specialized computer programs that will go ahead and solve these loop rules for you. You put in the components you want, you put in the loops that you want to take, and it'll just do the algebra. for you, and that's very convenient. But unfortunately, at this stage, yeah, you're still going to have to be able to do the simultaneous equations, do the algebra. But they're all worked exactly the same way. Get those equations set up. Use the loop rules. Use the junction rule. Remember the sign conventions, whether it's going to be positive or negative, whether the potential difference is going to be positive or negative. And then once, make sure you've got the same number of equations as unknowns. Once you've done that, you've done the hard work as far as the actual intelligence goes. The rest of it is, well, it's just kind of brute force and turning the crank to get to the end. But as long as you're careful, you'll get there. All right, so work on the practice. And if you've got any questions, as always, make a discussion post. But if you find you're not getting the answer that you should, there's a